concentration decline in some certain parts of the world. And especially also here in Scandinavia, and people thought about all the consequences for the organisms living in the aquatic systems, but I was more interested in some other global processes. So I was thinking about the calcium and the global carbon cycle, and we know that the calcium concentrations have a big impact in the oceans, where we have this calcium carbonate burial, and we also have some large lakes where we see this calcium carbonate burial. But we also have some other processes going on, and this is the carbonate system in aqueous solution, which means that we have bicarbonate in our systems, which is should be in equilibrium. And we all study this when we look at carbon dioxide, but now I wanted to shift a little bit into this bicarbonate story. And my thinking was, okay, bicarbonate follows a very nice theoretical pattern where you have a pH around 8 and a maximum bicarbonate concentration, and then you start having this carbonate, and you can get calcium carbonate precipitation in the lakes. So what is the role of calcium in this pattern here? I was thinking, okay, we have this carbon dioxide input from the atmosphere. We have more carbon dioxide in the oceans now, probably not that much visible in our freshwaters, but maybe we see some signals there. And then the calcium comes in when it comes to the calcium carbonate precipitation. But maybe the calcium has already a function when we go to the left-hand side of the equilibrium for the bicarbonate, or maybe also for the carbon dioxide. So the oceans are really well studied when it comes to the carbonate system, but the freshwaters are not really well studied. We have a few examples where we studied all this carbonate system, but not very many. So I was thinking, okay, if we have this equilibrium, then we should somehow see a relationship between the calcium and the bicarbonate, if everything turns out like being in the ocean and also being like the theory tells us. So I was interested, what is the relationship between the calcium and the bicarbonate? So I went out to the GLEON community and was collecting all the kind of sorts of data which are available. And each of these black dots here is actually a data point from where I receive data. So you see that it's a very efficient tool to get as many data as you want from a global perspective. And you can also see that I received quite a few data from sites where we don't actually have sensors, but where people collected data from other sources. So in the end, there were almost 500,000 of water samples, and we had 43,184 lakes, stream, and also riverside. So this is a real global approach, not only the lakes, but also the rivers, because I wanted to see on a global freshwater and from a global freshwater perspective how it looks like. And what we find now is that we have median concentrations of 4 milligram calcium per liter. This is really not a lot. We have a 2.5 percentile, which is very low, 0.4. And we have, it's not really the maximum, but the 97.5 percentiles is at 74.4 milligram. And then actually as many as 20.7% of all the water samples which we have now around the world, we have the critical low threshold value of less than 1.5 milligram per liter. And I tell this is, I name this as threshold value because when it's less than 1.5, it means that some organisms will die. They need this kind of amount of calcium to survive, especially also the Daphnia, and quite a few organisms. So 1/5 of our freshwaters in the world, they have actually a calcium depletion, which is quite substantial. But I was more interested, as I told you, in the carbonate system. So let's see what we see on this figure here. We have the pH on the x-axis, and we see that when we take all freshwaters of the globe from a global perspective, we actually reach pH values up from 2 up to a level of 12. And we see that the calcium concentrations, they have a maximum at a pH around 8. And we also see that they decline towards very low pH values and they decline towards very high pH values. And then we study the bicarbonate and look what is happening with the bicarbonate. And it looks pretty similar. And if you remember the theoretical carbonate system figure, which I showed in the beginning, it's actually exactly the same kind of figure which we see with our actual measured data overlapping with the theory, which means also the bicarbonate has a maximum at around a pH of 8, and it declines towards lower and towards the highest pH values. Then we have one lake which is quite special, and this is Lake Neusiedler in Austria. And people might wonder, oh, why do we have really proportionally very high bicarbonate concentrations in this lake? Well, the reason is that this is a very special lake. It's an endorheic lake where we don't have a real frequent inflow and outflow. And we might have more lakes in the world following this pattern. These are very special from a global perspective, very special lakes, because they are not connected to the global water cycle in the same way as our usual freshwaters are. So Neusiedler is a little bit an outsider, but it still follows the pattern. It's just a little bit shifted. So let's see what happens to the equilibrium, because we were thinking that calcium and bicarbonate should be in equilibrium. And if they are in equilibrium, then we should have a one-to-one regression line here. And if we have the regression line, we see, yeah, on a global scale, the points follow quite nicely the one-to-one regression line. We have this Lake Neusiedler, which is a little bit an outsider. But otherwise, it fits the pattern quite nicely. So this means on a global scale, we have an equilibrium between calcium and bicarbonate. But there's also a question mark because, yeah, if this is the case, then we should see this on a temporal scale as well. So what we should see is that calcium and bicarbonate, they should actually follow each other on a temporal scale now. Which means if you have an increasing pH, which a lot of freshwater show because we have a recovery from acidification, and they still remain below 8, which you see on the figure here, then we should see an increasing calcium and an increasing bicarbonate. For freshwaters with a pH more than 8, it would mean if we have an increasing pH, we should actually see a decrease in calcium and bicarbonate concentration. So this is what we checked with all the temporal data which we received now from the network here. And the temporal scale was from 1980 to 2017. We had 215 complete time series. And there were these patterns. Yes, we expected calcium and bicarbonate, they co-vary. But it could also be that they don't do it if there's something happening on the temporal scale. So let's see what the outcome is. Well, we have 77 sites that actually follow what we expected from the spatial scale, which is 36%. It's not so much. So most of the sites, they actually don't follow what we see on the spatial scale. They really don't show this co-variation. So something is happening actually on a temporal scale. So let's see what we have on the temporal scale. What is wrong here? The calcium significantly decreased in 52% of the freshwaters which we analyzed, which should not really be the case. And this scenario should only happen when pH decreases in waters with a pH less than 8. So this is something is not really working. That means calcium should increase and not decrease, as we all report and as we also see with our own data. So let's go back to the equilibrium conditions, which we found on a spatial scale, and analyze this a little bit more in detail. Let's see what the residuals are, because we still have residuals from the one-to-one regression line. What we see here is if we make this a little bit more in detail and look at the pH and relate the residuals towards the pH, we see actually we have a calcium excess in the low pH waters. And then we get towards equilibrium when we have a pH more than 7. So something is happening in our acidified lakes and rivers. So what happens there is that actually here is the calcium deviation in milliequivalent per liter plotted against the sulfide on a temporal scale, which means, yeah, if you have sulfide concentration, which the acid rain actually caused, then you move away from the equilibrium concentrations. So the sulfide deposition caused actually displacements of calcium from equilibrium conditions. And you see this in Sweden, you see this in the US, you see this in many, many regions where we had this acidification effect, which means, yeah, sulfide is something which actually disturbs all our natural systems here. And we can look at time series. This is the time series from one of the sites in Sweden, which showed the strongest decline in calcium concentrations. We see the sulfide goes down quite fast from 1980 up to now. The calcium follows this pattern. And if we determine the calcium deviation from the equilibrium conditions, which means that they're not in equilibrium with bicarbonate any longer, then we see we are now reaching the point that we are actually coming back, because the zero means that we don't have a displacement from equilibrium concentrations. So we are going back to natural conditions, but we caused quite a substantial deviation from here. So if you conclude all the different patterns here, which we get from the nice global data which we received via the GLEON network, is that we can conclude freshwaters play an important role in the global carbonate system. This is the first time that is actually shown. If you combine all freshwaters, you see that it perfectly follows a theoretical carbonate pattern, which was quite unexpected, because I was expecting much more deviations and much more patterns. And this is a perfect example that you see patterns which you only see if you combine all the different freshwaters. We would never ever have seen this for a small amount of data. So the second conclusion is then that calcium and bicarbonate are usually in equilibrium in freshwaters, which is also quite unique to show, because no one else has shown this before. The freshwaters are ignored in the Earth system models, but this is a typical example that they need to be included in the Earth system models, because they are much more important than we thought. And the third conclusion is that acid rain caused the displacement of calcium from equilibrium conditions. So we make actually, we are able to make anthropogenic impact, which is so large that we change the whole equilibrium conditions on Earth, which is quite substantial, and which is really nice to see with all the nice data. So that was an example of showing how the whole GLEON initiative makes and reveals pattern which we would never ever have seen if we studied just our own systems. So that's for now, and I think I've taken up almost my time, 2 minutes for questions, so you're most welcome to ask.
Thank you, Gesa. Indeed, are there any questions?